Hello, everyone, and welcome to We Meet at Digital Days. My name is Lisa Richter, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is flat wire inductors for electrical cars. Our speakers are Pablo Castillo and Carlos Farnos. They will hold a presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions during the presentation at any time. Nevertheless, you have the opportunity to ask the questions via the chat function, or better, the question parts. You will find the question window in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the presentation, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You'll receive the link for the presentation in the next few days, and the recording will be available at our website shortly. So now I will hand over to our speakers, and I wish you an exciting presentation.
Hello, everybody. I am Pablo Castillo, Product Manager in the Automotive Standard Products Division. I have been in the company for almost 4 years, and today I will present flat wire inductors for electrical vehicles alongside with my colleague, Carlos Farnos, also Product Manager for the same division and in the company for almost 4 years too. The agenda for today is the following. We will start speaking a bit about the automotive market trends. We will continue comparing round and flat wire. Then we will do a design example in which we will see what benefits we can get using flat wire. And last, we will show which are the different solutions Würth Elektronik can provide with flat wire. Let's start with the market trends. As we can observe these days, the tendency in the automotive market is to get higher power density, especially in the powertrain and high voltage stages. To this, we need to add the search for higher efficiencies and more reliable components. Then the challenge for magnetic manufacturing is to get smaller and lighter parts with lower losses as possible. It is also known that electrical vehicles are on the rise at the moment, as we can see a growth in sales of 70% for 2021. We should also add the expected increase in the sales in the following years due to the increasing government restriction to internal combustion vehicles, in which we have a clear example here in Europe. There is harder emission limit planned for 2025 with the new EU7 regulation, and more restrictive than that is the prohibition of internal combustion vehicles sale by 2035. Now, driven by this higher power density need in the circuitry of vehicles and the research for better efficiency, let us compare round and flat wires now. Round wire is the most used conductor in passive components because of its easier manufacturing process and versatility for many different core shapes. This translates normally in better prices. It can also bring some disadvantages, such as a filling factor inside the inductor that does not allow for a maximum use of the space because it is around normally 70%. It can also bring other disadvantages like higher DC and AC losses. Why does round wire have higher losses? There are two main reasons. DC losses. These are caused by the resistance of the wire, which cause Joule effect losses. This will be dissipated as heat, as you know, proportional to this resistance. As round wire has worse filling factor than flat, for an equal space and number of turns inside the inductor, round wire will typically have a smaller cross-section than flat, resulting in a higher equivalent resistance and therefore higher losses. Regarding AC losses, they are higher because of the skin effect. This is induced because of the circulating currents created inside the conductor by the alternating magnetic field inside it. These currents result in lower effective section in the conductor, as you can see in the image at the right bottom. The majority of the current then circulates then nearer of the surface of the conductor. That is why it is called skin effect. This effect is getting worse once we increase the frequencies. In the image of the left, we can see for different frequencies in a given conductor section how the skin depth diminishes the effective conductor section. The skin depth is considered from the outer part of the wire radius of the wire and measured to the inside of the part. So when the frequency is low, the skin depth, as you can see in the image in the left, is bigger than the wire radius. So all the section in the wire can be used. As we increase the frequency, the skin depth value decreases to a point in which it is smaller than the wire radius. We get then an effective section, which is the subtraction of the initial area minus the one created by the skin depth. So the resistance here can increase. Below that, we can see an example of the skin effect in flat wires. Here, we do not have an equal radius distribution in the wire, but two different sections, width and height. As height is much smaller than the width, the skin depth, in order to be relevant and decrease the conductor section, needs a very, very small value compared to the height of the wire. So a higher frequency can be used because the skin effect will not be that relevant. The consequence in both round and flat wire of the skin effect, even being more critical for round, is a reduction of the conductor section, creating an equivalent higher resistance and again higher losses, especially again in the round wire. Once we've spoken about the disadvantages of the round wire and done a comparison between losses of both wires, we can summarize that flat wire has some advantages. These are that we can get better space occupation in this wire because the filling factor is around 90%, much higher than before. As discussed, a better copper usage at high frequency than round, because it gets similar for a similar cross-section area, we get lower skin effect. We can find better stackability between winding turns, which leads to two different advantages too. The first of them is the better space occupation inside the conductor, as you can see in both images, a cross-section of a regular part. The second of that is that the windings are more repeatable and therefore the resistance value and parasitics elements are more constant throughout different parts. The last advantage of the flat wire is the better thermal management. Why is that? There are three different ways of dissipating heat. First of all, radiation, which is the less important method of the three here for inductors. Then convection, which is related to air or fluids. As air is, if not flowing, is a good heat isolator, the heat dissipation is very dependent on the environment or forced ventilation. And then conduction, which comes from the direct contact between hot parts of the inductor and the PCB. Here is where the flat wire is useful, because as copper is a great heat conductor, the bigger cross-section of the wire can make a big difference in moving the heat from the inductor to the PCB. Then, if we also combine a good layout and connection, we can create in the PCB a good heatsink. We can see here in the image in the right at the bottom, an example on how to measure and characterize the rated current of the inductor by the IEC 620242 Class D PCB. You can see here how a bigger wire section can conduct here alongside with a good layout. And using this method, as my colleague Carlos will later show you, there is a big impact in the rated current value. We have seen the comparison between flat and round wires and the advantages each one provides. There is great variety of application inside the car, which both wires can be used. But flat wire gets more important when the current demand and higher frequencies are required. For example, motor controls, power conversion, or battery management. We want to show you a design example for one of the most important applications in the car, which is the power conversion. There are many converter topologies that can be used, but for simplicity, we chose a typical buck converter. Here, we can see the typical buck converter schematic, in which all components are ideal. We don't have any DC or AC losses, there is no voltage drop in the diodes or transistors, and we don't have any parasitic RDC in either capacitors or inductors. We will keep in mind that the higher the switching frequency, the smaller our inductor can be because the lower ripple current that will go through it. Our design parameters will start by the following: an input voltage of 13.5, but could be from 5 to 36, a switching frequency of 400 kilohertz, an output voltage of 5 volts, and a maximum output current of 6 amperes, but it can go from 0. With this data and the formula to calculate the inductor needed, we obtain a value of 5.2 microhenries, and the nearest standard value is 4.7. For this reason, we will use a PDA 1216 of 4.7 microhenries for our example. This inductor is a shielded typically and qualified for automotive, and take into account that it is winded with round wire at the beginning. We chose that inductor because its saturation graph shows that it can withstand 6 ampere, which is the maximum output current, and the self-heating is tolerable for that current. We can say now that this PDA is fully usable and adequate for the application. If the circuit was ideal, there wouldn't be any difference in the circuit efficiency regardless of the inductor we would select. Either way, flat wire or round wire. But unfortunately, these non-idealities are there and must be taken into account. So let's consider them in order to do a good estimation of the maximum theoretical efficiency of the converter. All inductors have, as you know, equivalent series resistance created by the wire forming it. We will consider the PDA RDC, which is 14.5 milliohm. We will also consider a typical 4-volt voltage drop in the diodes of 0.7 voltage and a resistance of 30 milliohm, which are typical values. Transistors have resistance too, so we will use 41 milliohm. And lastly, for our calculation, we will use a second inductor at the input for filtering. After some calculations and plotting, we obtain the following graph. Take into account that both graphs are the same. The left one is the bigger picture and the right one is one zoomed in. It can be seen a high efficiency up to almost 97%, which is a little bit lower when the output maximum current is there. But then, after everything we discussed about flat wire and its benefit in higher current and higher frequencies than round wire, what would happen if we change this PDA for another inductor, similar but with flat wire, let's say the new XHMA? We can observe here a higher efficiency, up to almost 98%, which is the graph in the left. But is that big of a difference? Comparing the image in the right, which is the graph for PDA and XHMA, we see that there is not that big of a difference. So what is the trick? After everything we've spoken, is the flat wire that good? Well, the trick is that the chosen XHMA size is 6060, whose land pattern and volume is only 30% of the PDA 1260 we chose at the beginning, which is, as you can see in the image, quite big of a difference. So as a summary for this, flat wire inductors can allow for a dramatic inductor size reduction while maintaining electrical capabilities and performance. Also, then, if we want to compare one-to-one sizes between flat wire and round wire, the part with flat wire gives us a much higher rated currents. So then, now I want to introduce my colleague Carlos Farnos, who will take the presentation from now on. Thank you, everybody, for hearing.
Hello, everybody. Thank you, Pablo Castillo, for introducing me. And thanks, Pablo, for this nice exposition on the benefits of the flat wire. As we could have seen, flat wire offers many interesting advantages for your applications, from less DC conduction losses to better performance in AC, as well as other side benefits like less self-heating. As we saw in the converter example, another interesting point about the flat wire is that as it allows better space usage in the inductor, helping us in the miniaturization of components. The part we offered in the example was approximately 1/3 of the volume and required only 1/3 of the space in the PCB. This is very interesting when we are facing space constraint in the application. But even if we are not, it is important to highlight when we are facing space, highlight that a flat wire inductor will be able to handle more power to its equivalent one-to-one inductor made with round wire, either for increasing the density power or to reduce the operating temperature. There's an important advantage to keep in mind when selecting the inductor for your applications. For these reasons, in Würth Elektronik, we work to offer you a variety of flat wire products to suit all your needs. The first product we want to introduce you is the WE-CHSA. Its initials stand for Cube High Current Inductor S&D Automotive. On this slide, you can find a picture of the product and a transparent CGI to see the interior of the part. This part consists in an external cube of manganese zinc material, a rod core made also of manganese zinc, a base to ensure the rod core position, and the flat wire coil. This part is available in 3 sizes, 8x8, 10x10, and 12x12, with many different inductance values for each size, from 0.33 microhenries to 20 microhenries. Even though it is a very small part, it achieves saturation currents up to 57 amps for 30% drop of inductance. One of the key points of the product is its high reliability. We tested under ACQ 200 grade 0 conditions to ensure operability from -55 to 150 degrees. This means that it can be used in all places inside the car. What makes this part really special is its patented air gap fixation system, or in other words, the polymer base. With this advanced design, we ensure that the position of the rod core inside the part is always the same. And what's the benefit of it? We can offer a product with less variation in electrical characteristics from part to part. For example, the saturation curve from part to part will be very affected if the rod core is not perpendicular to the inner cube surface or placed upper or lower inside the cube. In addition to this, the base has another function in this component. We have just talked about the high degree of reliability the part can offer, and this is in part because of the nice coplanarity we can ensure with the base. As you can see in the picture, paths are embedded in the polymer base with excellent tolerance, and this will ensure the mount to the PCB and the mechanical resistance of the assembly. As we said, terminals are located in the bottom of the base, and it is in the bottom of the component, but it's not a problem to check the solder meniscus through an automated optical inspection in production. To achieve this, we extended the paths on the sides of the base and just check the recommended lamp pattern in the datasheet to ensure this process. We said that the outer cube is made of manganese zinc. Apart of offering a magnetic path, it has the function of shielding the winding, and it is very easy to find many different unshielded rod core inductors for automotive applications. But when radiated emissions are problematic, CHSA could make the difference thanks to this shielded construction. And of course, these are all extra benefits to the advantage we have just told you of the flat wire. Sorry. Okay. This year, we released a new part based on the previous product we have just seen, and it will be available in the same 3 sizes, 8090, 1011, and 1212. You can see we add 1 letter to the name that means performance. And what's the difference with normal CHSA? The main difference to normal CHSA is that the internal rod core is now made with an iron alloy material, but the outer cube remains on manganese zinc. And this changes the electrical performance of the part. For example, you can see that we have a maximum saturation current for this series of 48.5 amps at 10% drop of inductance value. And it might sound very similar to the value we saw for the normal CHSA, but it's very important to pay attention on the 10% drop, because saturation for normal CHSA is defined for 30% drop. So the behavior of inductance versus current in this CHSA performance is much better than in normal CHSA. It is important always when comparing different products to pay special attention on the percentage of the saturation current. At the moment, there isn't any standard industry to say at which percentage should be measured the saturation current, and it is normal to find saturation currents defined for 10, 20, or 30%. We must remark also that this part maintains ACQ grade 0 with operating temperatures from -55 to 150 degrees. And what does the iron alloy rod core do different? It improves the saturation capability. Manganese zinc normally exhibits hard saturation curves of inductance versus current, but in an iron alloy, inductance decreases slowly when current is increased. This makes it ideal when high current during transients are expected to appear in the application. For example, in microprocessor filtering and in lighting application. For those who are not familiar with hard saturation and soft saturation terms when referring to inductors, we have prepared a graph to see the difference. In the graph, we compare two equal inductance of 8.2 microhenries for CHSA and CHSA-P size 1212. Red line corresponds to normal CHSA, and black line corresponds to CHSA performance. In hard saturation inductors of materials, the inductance normally is constant when the current is increasing till some point it suddenly decreases abruptly. In soft saturation material or inductance, the inductance value normally decreases little by little when the current is increasing. In some cases, if we know that the maximum current of the application is far from the saturation point, normal CHSA is more interesting because the inductance will be higher. In case of some high current spikes are likely to appear, it will be more interesting to choose the performance version. We'll have more inductance value. We wanted to show you the suitability of this product to be used as a filter besides as a power inductor. On the graph on the right, we could see the expected attenuation in dB when applied to power lines or data lines of different impedance, from 1 ohm to 90 ohms. And this makes it interesting as an input filter in DC-DC converter or DC mode of filtering, for example. Let's move to the next member of the WEA portfolio. This time we have the 8CIA, that means high current inductor automotive. This product derives from our very successful industry product, WE8CI. Optimizing production with latest automation technologies, we could finally bring this product to the automotive industry. 8CI, it is available in size 1050, 10 by 10 millimeters, and 5 millimeters height. We will find 11 different inductance values in this versatile family, from 0.722 micros to 16.7 microhenries. This inductor is made of 2 cores of iron alloy powder assembled together with flat wire coil. As we saw with the CHSA, using very similar composition for the core, we have same soft saturation in this product. This is important also to say that this material is very stable versus temperature, and we shall expect no difference in inductance and saturation, no matter if it is working at maximum or minimum temperatures. And this part is also ACQ grade 0 qualified, so maximum and minimum temperatures are -55 degrees to 150 degrees. We can see that the flat wire is bended around the bottom of the part to conform the terminal. This direct connection of coil to PCB minimizes total RDC and therefore the conduction losses. For example, we could find a part with only 1.26 milliohms. As my colleague explained before, it will help to start some heat out of the inductor and use the PCB as a heatsink when proper trace width and thickness is used. For this product, we have also a shielded construction that will help to reduce radiated emissions. For this reason, this inductor is a very good option for high current DC-DC converter or filtering. Here, you can see a brief summary of the key electrical characteristics of the family, saturation and rated current. Please notice that to be able to show all inductance values together in the saturation chart, we needed to apply logarithmic scales. All this data is always available in our online tool TreatExpert, and it will guide you to select the best inductor in every case, showing you the AC losses as well as the DC losses for every operational point. It is time now for WE-XHMA, our extreme high current molded inductor automotive match code. If you remember, this is the part we use in the converter example. This part is constructed with a vertically winded flat wire coil. Inside of an iron alloy powder solid body. Then the wire is bent out of the body to conform the terminals. And thanks to this construction, we have again direct connection between coil and PCB. We have many different sizes to match your requirements, from the smallest 6030, only 3 mm high, to the big 1510, including some middle options like 6060, 8080, and 1090. In total, distributed in these 5 sizes, we have 33 different inductance values. This product is also ACQ grade qualified grade 1, with operating temperatures from -40 to 125 degrees. As you can see in the picture of the product, there is a small dot on the corner of the component. This is the start of winding marking. It is very important to take this marking into account when mounting the component in the PCB. This marking is telling us which of the two terminals is connected to the first turn inside the part, the turn closest to the terminals. If we connect this terminal to the switching node in the circuit, we can help reducing the radiated emission even more, because part of the coil will be shielded via the other turns above this and the rest of the body. Its high current capabilities, combined with its reduced size, makes this part ideal for maximizing the power density in high current converters. Here you have an example of the saturation curve for the 1510 size. Please notice again the use of the logarithmic scales for both current and inductance. You will find complete information about all the parts in our online catalog and simulation tool RedExpert. On the right, there is a very interesting graph. We previously said that when combining the flat wire with an appropriate lamp pattern, we could take the advantage of the big cross-sectional area of the flat wire to extract some heat from the inside of the part and dissipate it through the PCB. These graphs, we can see the comparison of the cell heating of the part when measured on a 35 micros thickness copper PCB, or in a IEC 62024-2 Class D PCB, which is the red line. Rated current increases from approximately 70 amps to 30 amps for the same part. This is a good example to show how to take advantage of the flat wire used in this part. Under favorable conditions, the cell heating of the part could be dramatically prevented. And it is important to have some small consideration here. The part has been measured in steel air. It gives even more margin to improve the cell heating and removing the heat, but at the same time, it was not sharing space in the PCB with other sources of heat, as transistor, for example. The important idea here is, if it is needed, it is possible to achieve less cell heating and better cooling that the datasheet suggests for the rated current. The value in the datasheet is a reference only, because it is not possible for us to try all possible combination of PCB layout, current, enclosures, and other heat sources. And the last member of the automotive flat wire family, WESCFA, high current flat wire inductor automotive. This time, we don't have iron alloy anymore. In this case, we have a manganese zinc PQ core. This inductor is the biggest in the automotive portfolio and designed to handle very high current with saturation currents up to 81 amps, 81 amps. Its dimensions are 28 by 28 millimeters and 17 millimeters height. Due to the use of flat wire, we can achieve ultra-low RDC values of 0.6 and 1.1 milliohms. We have 6 different inductance values for this product, and might be surprising that we have only 2 different RDC values, and that's because many of them share the same coil, and the difference is only in the air gap of the core. If you look closely to the picture of the product, you will see that the wire is welded to a plastic base. The reason to do that is because it is very difficult to ensure good coplanarity tolerances if we rely on the wire only. And it might happen also when handling the part in the assembling process to PCB that some of the terminal is bended and then they are not soldered to PCB. The base solve all these problems, offering a product with perfect coplanarity. We can see also that the presence of a third back pin and this pin is not electrically connected to the part. But as it is very big and very heavy, it improves the mechanical stability of the part when soldered to PCB. This product has been optimized to operate in the range of 0.2 MHz to 1 MHz. Through the help of our online calculator tool, RedExpert, you will be guided to select the best component for your application. This product will be ideal for converter and inverter application, as well as DC motor controllers. Last but not least, we can have a look on the electrical performance of the family. And we can see we have suitable inductor for saturation currents from 14 amps to 81 amps. Thank you everybody for joining this presentation about flat wire, and we will remain here for answering your questions if you have any. Thank you everybody.
Yes, thank you very much, you both, for your presentation. Like you already said, we will now take our attention to your questions. You've got the opportunity to ask the questions via the chat, or better, the question window in the panel. I thought there are already questions. Maybe we can start with the first one. WEHCIA, is iron powder alloy core conductive?
Yes, it is conductive, but it is coated. So it's not a problem if you have traces, but don't put sensitive traces just below the part in the PCB.
Okay. Great. So maybe we can go to the next question. At the end of the converter example, you compared a flat wire inductor and a round wire. Flat wire was much smaller. Is the coil the only thing that makes a difference?
Well, there was many differences between these two parts. One is the flat wire, of course, and the other is the material of the core. One is ferrite and the other is iron powder. But for example, in the automotive portfolio, we don't have an inductor to do one-on-one comparison, but we do have in the industry portfolio. And for example, we have a similar part as the round inductor we saw, and we can achieve exactly same electrical performance with a decrease around 20-25% in size and volume.
Okay, thank you for this answer. So let us check if there are any other questions. So next one, it is said that skin effect is worse in round wire, and that was the reason to move to flat wire. But what about Litz wire? It should be the best option?
Of course, Litz wire is made a strand of very, very small, thin wire. So for this case, you will have almost zero effect of the skin effect. But normally you will have problems with the highest is the frequency. So the thing is, if you move to this wire, you will use a lot of cross-sectional area for the insulation between every single strand. And at the end, you will have less copper. So we need to take into account that when we raise the frequency, the ripple on the components, it will be much smaller. So for example, in a converter, DC losses will be higher than AC losses. So flat wire will be normally better. The only moment in which Litz wire will be better if we have very, very high ripple. In any other cases, flat wire will be perform better.
Okay. So I think there's one last question. What is the failure mode for the molded inductor?
Oh, the failure mode. It will be interesting to extend a little bit this question because it's to open. I don't know if it is referring to electrical failure or mechanical, or I don't know exactly.
Okay, I think in that case it will be better maybe to the person who asked the question, you can send us an email and ask us this question again with details. So the colleagues will answer this per email. Great. Okay, so there's one more. Maybe we can do this. Also, you mentioned that WXHMA as composite material core. So is it iron powder based or rather metal alloy based?
Is a iron powder alloy.
Okay, great. So hopefully this helps. I think now we answered all the questions, but if there are any other questions left, just mail us. And then we can hand it over to our presenters. So Pablo and Carlos, thank you very much for your presentation. This was really interesting. So I think now I just want to give you all one hint. So I will show my screen so you can see the next presentation, which will start tomorrow at 9 o'clock. With the topic EMI debugging of a low power buck converter with Frank Puhane. Yes, hopefully see you there. Thank you very much for being here today, and yes, have a nice evening.
Thank you. Have a nice evening. See you.
Bye.